Okay, so the story that we want to think about today is the story of impulse and momentum. And just like when we talked about work and energy, the motivation for studying work and energy was to analyze situations that we just couldn't do just with kinematics and dynamics. And the story continues here when we're talking about impulse and momentum. We're talking about situations that would be a little bit more demanding to analyze with kinematics and dynamics. And it becomes easier to think about, and it gives you more insights if you think about other quantities that are derived from the kinematics and dynamics variables. And these are the impulse and momentum stories. You might have heard the word momentum in regular speech. We use the word momentum all the time. I guess back when we had like sort of professional leagues for things, you'd say things like, I don't know, the Houston Astros had momentum. Well, we know why, but you would say things like that. They had momentum, and they had momentum really was interpreted as something like they're difficult to stop. They're on some sort of streak and they have momentum. Because you could also have a losing momentum, I suppose, a losing streak. So momentum, I suppose, is about something that has to do with being hard to stop or hard to change. I think that's a good way of thinking about momentum. And it's a similar way that we think about it in physics. And if you think about two objects, one of them less massive than the other. So let's say I have a bicycle and a truck and they're both moving at 20 miles an hour. Which one is harder to stop? Obviously the truck is harder to stop. So the more massive the object, the harder it is to stop, and therefore the bigger its linear momentum is. The faster the object is moving, also the harder it is to stop. So if you think about a truck that is moving at 20 miles an hour and truck that is moving at 60 miles an hour, which one is harder to stop, then you can figure this out. So this is what we call the linear momentum, P, or for short, momentum. Until you study angular momentum, there's no other thing called momentum. So this is the thing that is called momentum. And we use the letter P because momentum, I suppose, used to be called impetus. And I believe that's where the P came from. M is the mass of the object. And the more massive the object, the bigger the momentum. So as the mass goes up, the momentum goes up. And V represents the velocity of the object. Notice the arrow here. This is a vector quantity. So the velocity is a vector quantity, meaning the direction is important. So that means that the momentum, because it's only a scalar multiplied by a vector, so you're scaling that vector. The velocity vector is like this. That means the momentum is a scale of it. So the momentum then would be a scaling of the velocity vector, which means it's in the same direction as the velocity. So the linear momentum is a vector quantity that has the same direction as the velocity vector. What are the units for momentum? Well, if you think about the SI units for the definition of momentum here, the mass would be defined in terms of kilograms, and the velocity would be in terms of meters per second. That's the SI units. So the momentum then is in units of kilograms, meters per second. And like I said, this is, you look at an instantaneous moment in time, right? You just say at this particular instant, what is the momentum of this object? And then maybe the object speeds up or slows down, so it has a different momentum now. Speeding up, then it has a different momentum, and maybe the direction of the momentum also changed. So there's a change in momentum of the object. This is some momentum initial, and this is some momentum final. So the momentum, just like the velocity, describes an instantaneous situation. At this point in time, this location, at this point in time, at this instant, what is the momentum of the object? Let me tell you the other story about the impulse. So we're going to get to know this new character. And then these two characters, the momentum and the impulse, are going to interact later in the story. So the work, if you remember, was the force multiplied by the displacement. So it's sort of an accumulation of the force over displacement. As the object is moving, a force being applied to it like this, and you want to find out the work done by that force, you say, how far did this object have to move while the force is being applied and so on. And that's really what gives you the work. The impulse quantity, which is, we use the letter J to talk about the impulse, is the accumulation of the force over time. So how long did you apply this force for, multiplied by that time? So this is some sort of time of application of the force. If I say force times time, that gives me a quantity called the impulse. And if you think about the force being a vector quantity and the time being a scalar quantity, then the impulse then has to be a vector quantity. Again, I'm scaling the force by some scalar here. So that means that the impulse is in the same direction as the force. And the SI units for impulse then would be the SI units for force, which is newtons, times the SI units for time, which is seconds. So the impulse would be in units of newtons times second, which if you want to put it in the base SI units, then you would say Newton, I know, is kilogram meters per second squared. And then I multiply by seconds. So one of the seconds goes away and I'm left with kilogram meters per second, which if you remember, the momentum was in units of kilograms meters per second as well. It's the same units. So the impulse and the momentum have the same units. Okay, so far we've defined two things. We've defined momentum and we've defined impulse. And these two things are related in the way you're going to see in 1 second. So start from the top left corner here. We're thinking about Newton's second law. The net force is equal to the mass times the acceleration. And then you say, but I know that the acceleration on average, the final velocity minus the initial velocity divided by the time. That was the definition of average acceleration. So I plug this in here and I'm left with this piece, that the average net force is equal to the mass times the final velocity. That gives me this term. The mass times the initial velocity gives me this term, divided by delta t. So if I multiply both sides by delta t, I get that the average net force times time is equal to mass times final velocity minus mass times initial velocity. So for example, the example that's shown on the left here, you have a baseball that is coming in with some velocity. It's in contact with a bat, and that provides this force that is acting on the ball. That's the net force acting on the ball. And this net force acts for a certain amount of time to change the velocity from initial to final. So using Newton's second law, we found out that in the end, how much force was applied to the ball multiplied by the time of contact with the ball during this phase is equal to the mass of the ball times its final velocity minus the mass of the ball times its initial velocity. So this right-hand side of this equation is talking about the beginning state and the final state, right? 1 and 2 here that are labeled, final and initial. So that's the right-hand side. It's talking about the state at the beginning and the state at the end. It's talking about how big was your momentum to start with, right? Because remember, mass times velocity, that's momentum. So how big was your momentum to start with? Now, how big is your momentum at the end? The difference between these two is this piece in the middle here. It's talking about how much force did you apply for how long. That changes the momentum of the system. So you can write this equation like this. You say, I just copied the equation from the slide before, but I know I recognize this as being the impulse, J, and I recognize this as being the final momentum, and this is the initial momentum, so I can write it as final momentum minus initial momentum, which I can also write as the change in momentum. And this is known as the impulse momentum theorem. Let's summarize this theorem here in the margin. Let's just summarize what the theorem is saying. It's saying, suppose an object is moving with some velocity initial, and it has some mass m, and then something happens to it. A bunch of forces act on it such that the net force acting on it was sigma f, and that changed its state of motion. Now, what this theorem is saying is, I can tell you how much your momentum changed by if I know what kind of force you applied for how long, or the other way around. If I know what your beginning momentum is and your final momentum is, I can tell you how much force you applied for how long. What happens during some sort of event is related to the change in this quantity from before the event to after the event.